Good evening, everyone. So, in the last class, we discussed about the integrals and some of the applications of integration. Today, we'll be discussing few more applications about the integration. The one of the important application of integration is that we use integration method of integration to calculate the average of any function. To calculate the average of any function. So we use the integration to calculate average of a function for any function. Suppose that our function is f of x, and we need to find the average of this function between the interval a and b. Between this interval, we want to find the average of this function. Then how do we find the average of this function? This is how we represent average of a function. We integrate this function with respect to x, and this x variable can be anything. Between the limits a and b, we will always take the limits between the limits will be taken in such a way that suppose we want to calculate the average between a and b, then the limits will be between a and b upon integral of dx, and once again the limits will be between a and b. So this represents nothing, it represents interval. It represents interval between which we have to calculate the average of a function. Let's suppose we have this Cartesian coordinate system here. This is a y-x plane. This is a y-x plane here. And suppose in this plane we have a function like this. This is our function. And suppose this function runs from x equal to a to x equal to b. From x equal to a to x equal to b. So this will be the area enclosed by this function. This will be the area enclosed by this function. This is the area enclosed. And we know the area enclosed by any function is given by the integration of f of x dx between the intervals like here a to b. But this will be the area enclosed by this function. Now if we divide this area by its interval b to a, that's b minus a, we'll get the average of this function. We'll get the average of this function. That's how we calculate the average of different function and what it actually represents. So this part of this average of a function represents area under a curve. Area under the curve between the intervals a to b. And this represents an interval. This represents an interval. Let's suppose that we have a function like this. This is the function given here. Class 12 will be studying about the AC currents, where current is a function of time. And then we are supposed to calculate the average current between different time intervals. Now here we have been given the current as a function of time. That's I is equal to I naught cos of t. I naught cos of t. And we need to calculate the average of this particular function between the intervals 0 to pi by 2. 0 to pi by 2. So our interval runs from 0 to pi by 2. This is our interval, right? So what we'll be doing is that we have to calculate the average of this I. We'll integrate this I naught cos of t with respect to variable t between the interval 0 to pi by 2. 0 to pi by 2. So I naught is a constant here. It will come out of the integration, and we'll integrate this cos of t between 0 to pi by 2, and integration of dt with respect to t, it will be t. So with the limits 0 to pi by 2. We know the integration of cos t is nothing but it is sin t between the limits 0 to pi by 2 upon pi by 2 minus 1, pi by 2 minus 0. So average of this function will be nothing, I naught sine of pi by 2 minus sine of 0 upon pi by 2. Sine of pi by 2 is nothing, it's 1. So we'll be left with here I naught pi and the factor 2 here. So the average of this I will be nothing, twice I naught upon pi. So this is how we calculate the average of this function. How do we geometrically see it? Let's suppose that we have this Cartesian coordinate system here. And in this plane, we want to plot cos of t as a function of time. So the graph of cos of t will be like this. So this represents y is equal to I naught cos of t. Here I naught here, it's nothing, it represents the amplitude. That's the maximum value of this function, amplitude. So we have this value here I naught. The same value will be here minus I naught. 0 to pi by 2. This is 0 here. This is pi by 2. 0 to pi by 2, the area enclosed by this cosine graph, cosine term will be this. This is the area. And what does this area represent? Area is calculated by I naught cos of t, integrating it between the limits 0 to pi by 2. That's what we have done. And then what do we do is that we just divide it by the interval pi by 2, we'll get the average of this function. So that's what average of this I naught cos t represents. So let's move on to one more question. Let's suppose that v represents our velocity as a function of v represents our velocity, and it's nothing, it's given the first derivative of position vector or displacement. That's dx upon dt. Now, if we integrate this velocity with respect to time, integrate this velocity with respect to time within limits t1 to t2. Now, what does this represent? Integral of v dt with respect to time? It represents, it tells us about the displacement. It gives us information about the displacement under the velocity time graph. Let's suppose that our velocity time graph is like this. Between the interval t1 to t2, this is our time interval. T1 to T2 is the time interval, and this is the area enclosed by this velocity time graph. And this area, once again, we know we'll be calculating this area using this integral. If we integrate this velocity with respect to time, within the limits t1 to t2. This is the area of this curve, but this represents displacement. This gives us the displacement, right? This gives us the displacement. Now, if we divide this area under the velocity time graph, it gives us the total displacement traveled by this particle. And now if we divide this total displacement traveled by the particle with the time interval, it will give us the average of this velocity. So it will give us the average velocity. Average velocity. So integrating velocity with respect to time within the limits t1 to t2, this represents a displacement of a particle. And if we divide this total displacement traveled by the particle with the time interval, that's integral of dt within the limits t1 to t2. This will give us the average velocity. So area under the velocity time graph, area under the velocity time graph represents displacement, and dividing it by the time interval gives us the average velocity. Similarly, we have this question here. In this question, the velocity time graph of a car moving along a straight road is shown in figure. The average velocity of the car in first 25 seconds. So this is the velocity time graph of car given in this graph. So if we calculate the area for this velocity time graph, this will represent nothing but the displacement. This will represent a displacement. And if we divide this total displacement between with the time interval 25 seconds, we'll get the average velocity. And we know that it follows a regular geometry. It's a trapezium. The shape of this graph is a trapezium. It follows a regular geometry, or we can also break it into three shapes, two triangles, this one, and the one rectangle. And we can add all the three areas to get the total area. It means that it will give us the total displacement. And if we divide the total displacement by the total time interval between 0 to that's 25 seconds, we'll get the average velocity. So area here of this trapezium is, area of trapezium is given by sum of parallel sides multiplied by the distance between these parallel sides. We can see this side and this side, these are two sides parallel to each other, and the length of these sides is nothing, it's 20, and distance between the parallel sides uh, just a minute, we're talking about the trapezium, right? We're talking about the trapezium. So this will be the one side. Let's suppose this is AB, and let's suppose this is CD. So here AB is parallel to CD. So these are the parallel sides of this trapezium. So between A to B, the length of this trapezium is 20 minus 10, that's 10, and multiplied 10, 20 minus 10, that's 10, and another side of this trapezium is 0 to 25, so it will be 25. That's the sum of parallel sides and distance between them. And the distance between them, these two parallel sides AB and CD, they are separated by a distance of 20. So we'll multiply it by 20. So total area will be 35 multiplied by 20. That's nothing. That's 700, right? 700. So average velocity is nothing. That's the total displacement. That's 700 upon the total time interval. That's 25 seconds. We'll multiply it divided with the 25 seconds. So we can just write it 7 into 100 upon 25. We can just cancel out it with 4. So 7, 4, it will be 28 meter per second. That's the average velocity between the time interval 0 to 25 seconds for this curve. So once again, this is an application of integrals. Now let's suppose that we have not been given a graph between the velocity time graph. We are given with the velocity as a function of time or acceleration as a function of time, then how do we calculate the average velocity or average acceleration uh, through the concept of integration? Let's suppose that we have been given a particle here. A particle is moving with velocity given as 3t square plus 4t cube. The velocity of the particle is 3t square plus 4t cube plus 4. And the question is asking where to calculate the average of this velocity between the time interval that is 0 to 2 means 2 seconds. So what we will be doing is that we'll just integrate this velocity as a function of time with proper limits. The limits are here 0 to 2 seconds and divided by the interval 0 to 2 seconds. So it will be 3t square here, 4 plus 4t cube plus 4 upon the integral of dt will be t. So we'll be getting the interval as 0 to 2 minus 0, that's 2. So we're just doing 1 upon 2 integration of this term with respect to time. So it will be nothing. Integration of t square with respect to time will be t cube upon 3. So it will be 3t cube upon 3. And the integration of 4t cube will be 4t4 upon 4. And the integration of 4 with respect to time will be 4t within the limits 0 to 2. So we'll get our average as, that's nothing, 3t cube upon 3 plus 44 upon 4 plus 40 with the limit 0 to 2 upon 2. And this 3 and 4 will go. We'll be just substituting the upper limit and minus lower limit. So 2 cube here will be 8. And 2 raised power 4, it's nothing, it's 16. Plus 4 into 2 will be once again 8 upon 2. So we'll be left with 16 plus 8 is 24. And 24 plus 8 is 32 upon 2. That's 16 meter per second. This is the average velocity of this particle between the interval 0 to 2 seconds. That's how we calculate the average velocity. If the velocity is given as a function of time, we will just integrate this function with respect to time with the proper limits and divide it by the time interval. We'll come to know about the average velocity. And in the similar manner, we can also calculate the average acceleration. If we have to calculate the average acceleration, let's suppose that in kinematics that we have been given acceleration, right, as a function of time. We know acceleration is nothing, it's the first derivative of velocity with respect to time. And if we have to calculate the velocity as a function of time, we just integrate the acceleration with respect to time. We get to know about the velocity at a later time t. So that's how we calculate the velocity at different times from 0 to t. Suppose the initial velocity is u, not, and final velocity is v. So this once again represents area under AT graph. Area under AT graph, that's acceleration time graph. So area under acceleration time graph will give us nothing but the change in velocity. Change in velocity. That's the one information that we get from the area under the acceleration time graph. One more important point is that if we have to calculate the average of this acceleration, what we'll do is that we'll just integrate this with the time interval 0 to t and divide it by the same time interval 0 to t. That's how we'll calculate the average acceleration also. Let's suppose that our question is that acceleration is given as a as a function of time is given as 3t square plus 2t. Now the question asks us find the average of acceleration or find the average acceleration, that's a average between 1 to 2 seconds. 1 to 2 seconds. Between 1 to 2 seconds. So what we'll be doing is that we will just integrate this function with respect to time, plus integral of 3t square plus 2t with respect to time within the interval that's 1 to 2 upon integral of dt 1 to 2. So integration of t square is nothing, it's t cube upon 3. 3 and 3 will get cancelled, we'll be left with t cube here. And integration of t with respect to t, it's t square upon 2. 2 and 2 will once again get cancelled, we'll be left with t square here. And the integration of dt with respect to time, it's t, so it will be 2 minus 1, that's 1. We'll be left with 1 here. The limits here 1 to 2, right? We'll be having here 2 cube, it will be 8, plus 2 square, it will be 4, then minus 1 cube, that will be 1, and minus 1 square, that will be once again 1. So it will be 12 minus 2, that's 10. So 10 meter per second square will be the average acceleration between the interval 1 to 2. So this is how we calculate the average acceleration, how we calculate the average velocity of different functions. If the velocity or the acceleration is given as the function of time, that's how we calculate the average of different functions. So this is one of the most important application of integration or integral calculus. Until now, I think most of the applications of integrations has been done, and we'll be moving to study some standard graphs. Generally, we encounter in physics, and some of them are like we should know about the straight lines. What are the equations of straight lines? What are the standard equations of ellipse or parabola and circle also, and even exponential functions. What are exponential functions and what are exponentially decaying functions? All these functions or the curve of all these functions we should be very much aware about, because these functions are very frequently used in physics. So these functions are very important for us. सम स्टैंडर्ड ग्राफ्स, कुछ स्टैंडर्ड ग्राफ्स जो है हम स्टडी करेंगे, जिसमें हम पर्टिकुलरली स्ट्रेट लाइंस, सर्कल या इलिप्स के बारे में थोड़ी बहुत इंफॉर्मेशन, जितनी हमारे लिए सफिशिएंट है पर्टिकुलरली फॉर फिजिक्स स्टूडेंट्स, उतनी इंफॉर्मेशन यहाँ पे हम डिस्कस करेंगे अबाउट स्ट्रेट लाइंस, इलिप्स एंड parabola, exponential functions, and hyperbolic hyperbola also, rectangular hyperbola. स्टैंडर्ड, सम स्टैंडर्ड, हम ऐसे लिख सकते हैं ग्राफ्स ऑफ सम स्टैंडर्ड फंक्शंस. Graphs of some standard functions. फर्स्ट को जो हम स्टडी करेंगे इट विल बी इलिप्स. इलिप्स के बारे में देखेंगे. This is how somewhat like ellipse looks like. And ellipse में मानता हूँ कि this the center of this ellipse is placed at origin. This is our origin. This we call as minor axis. and this we call as major axis. This is the major axis. There are two fixed points in an ellipse, and those fixed points, let's call this F1, this is F2, and these fixed points we call as foci. And suppose we have any point P on this trajectory, that's ellipse, and if we calculate the sum of distances from these two fixed points that we call as foci for any point, it's a constant. So sum of distances from two fixed points that we call as foci for any point, it's a constant. That's what we actually understand by the ellipse. It's a locus of points for which the distance from two fixed points, sum of distance from two fixed points is a constant for all the points. So this is the ellipse, what we call as ellipse. And this is a minor axis here, and half of this minor axis, suppose that is represented by A, and half of this major axis is represented by B. That's what we call as B as semi-major axis, or A as semi-minor axis. And the equation of this ellipse is given as x square upon A square plus y square upon B square, that's equal to 1. This is the standard equation of an ellipse which is centered at origin. The equation of an ellipse which is centered at origin. Equation of ellipse with center at origin. So this represents equation of ellipse with center at origin. P is the semi-major axis and A is the semi-minor axis. It depends upon the form of equation, which axis will be the semi-major and which axis will be the minor axis and which axis will be the major axis. It depends upon the equation of the given ellipse. Let's suppose that we have been given equation of ellipse like this. That's x square upon 16 plus y square upon 36. If we compare it with the standard equation of ellipse, that's x square upon a square plus y square upon b square, that's equal to 1. So 36 b square is equal to 36. So from here b comes out to be 6. Length of the b comes out to be 6. And similarly, if a square is equal to 16, if we compare between the two, a comes out to be 4. So we can clearly see that b is greater than a. B is greater than a. So we can say that b is the major axis. B represents the semi-major axis. B is the semi-major axis, length of the semi-major axis, and a is the length of the semi-minor axis. We can also plot this. Can also plot it like this. Since B is our major axis, represent the major axis, so it will be like this. So this is our ellipse. This is how this ellipse will look like. Let's move on to the next question, that if the length of a major axis is given as 5, and minor axis is given as 3. Write the equation of ellipse centered at origin. So it will be nothing x square upon it's given as 3, so it will be 3 square here. So it is given as 5. It will be 5 square, that will be equal to 1. So a standard equation will be x square upon 9 plus y square upon 25. That's equal to 1. That's equal to 1. So this represents our, these are the equation of ellipse. So this is the equation we need to remember, that x square upon a square plus y square upon b square equal to 1. If this is the form of equation we get anywhere, so we can clearly conclude that this represents an equation of ellipse which is centered at origin, where a and b can be semi-minor axis or semi-major axis. Let's suppose that if a is equal to b, means semi-major axis and the semi-minor axis are equal, then it represents a circle. Then it represents a circle centered at origin. Centered at origin. Let's suppose this is the circle. Let's suppose x naught comma y naught is the coordinate of center C and r is the radius of this circle. And the equation of this circle will be nothing, x minus x naught whole square plus y minus y naught whole square, that's equal to r square. So this is the equation, standard equation of a circle whose center has coordinates x naught and y naught. Suppose this x naught comma y naught is 0 comma 0, means the center is at origin. The equation of the circle will be nothing, x square plus y square is equal to r square. So this represents the equation of a circle which is centered at origin. So some of these standard equations we must be familiar with, and we must remember this equation. What are the standard equations of different trajectories? The trajectory here is circle, and the trajectory we studied before is ellipse. Suppose we have a function like e to the power x. We call this as exponential function. One of the important property of this function is that there is no value of x for which the value of y will be 0. Even if we put the value of x here is equal to 0, value of x equal to 0, we'll get the value of y equal to 1. And even if we put the value of y tending to infinity, x tending to infinity, y will be tending to infinity. And even if for x less than 0, if the values of x are negative, if we take the negative values of x, suppose value of x is equal to -2 or -3. Let's take x equal to -2. The value of y will be 1 upon e to the power 2, right? So this function will not become 0 anywhere. So it will not touch 0 Or we can say just like that, if the value of x becomes minus infinity, means we have our value of x approach to minus infinity. If x approaches to minus infinity, then only our y approaches to 0. If the value of x approaches to minus infinity, we can see that as we increase the negative value of x, the value of y decreases, but it does not become 0. But as we increase the value of negative value of x to the minus infinity, so the value of y will approach to 0. And as the value of x approaches to plus infinity, the value of y approaches to infinity. So that's how we can plot this. With this information, this much of information, we can easily plot this. This is also called as exponentially growing function. And one more important point about this function is this function cannot have negative values. We cannot plot this function in third or fourth quadrant. There's no value of x for which the value of y will be negative. So this function will always have positive values. Even if the value of x is negative or the value of y is positive, the output will always be greater than 0. It will not be less than 0. It cannot be negative. So this function can never be plotted in third and fourth quadrant. So we know that at x equal to 0, at x equal to 0, the value of y was 1. Value of y was 1. And it was exponentially increasing as x increased in the positive direction. And it was exponentially decreasing. It was decreasing function. It was decreasing with x in the negative direction. And it becomes 0 at minus infinity, or we can say it approaches 0 at minus infinity. So the behavior of this function will be like this. So this is what we call as the exponential function, or y equal to e to the power x. And this is the point where x is equal to 0 and value of y is equal to 1. So here at infinity, this function will touch at infinity with the x-axis and will approach 0 at minus infinity. So this is how we plot the exponentially increasing functions. And similarly, if we have a function like this, e to the power minus x, once again, there is no value of x for which the value of y will be negative or 0. There is no value of x for which the value of this function will be 0 or negative. But this function will be a decaying function. This function will be a decaying function. So this how this function will behave means this e to the power minus x, when x tends to infinity plus infinity, this function will approach to 0. This function will approach to 0. Or when this function, the value of x approach to minus infinity, this function is going to approach plus infinity. So the behavior of this function will be like this. So this is how this exponentially decaying function is going to behave. So this is nothing but y is equal to e to the power minus x. Now this once again, the value of y here is 1 at x equal to 0. So this is what we call as decaying function. This is decaying and this is growing. इन फंक्शंस की एक इम्पोर्टेंट एप्लीकेशन हमें फिजिक्स में ऑलमोस्ट हर जगह मिलती है, लाइक इन कैपेसिटर्स। जब हम कैपेसिटर्स को चार्ज करते हैं, दे चार्ज लाइक एन एक्सपोनेंशियल फंक्शंस। वो बहुत तेजी के साथ चार्ज हो जाते हैं कैपेसिटर्स, एंड देन दे सैचुरेट, और वो फर्दर चार्ज नहीं होते हैं। एंड इन द सेम फैशन, जब कैपेसिटर्स को डिस्चार्ज करते हैं, तो वो एग्जैक्टली एक्सपोनेंशियली, बहुत ही डिकेइंग रेट के साथ, ज्यादा डिकेइंग रेट के साथ वो चार्ज को लूज करते हैं, या वो डिस्चार्ज हो जाते हैं। दैट्स हाउ द कैपेसिटर्स आल्सो बिहेव एज अ डिकेइंग फंक्शंस, और द how that's how the decaying function or the growing function or the exponential function has applications in different parts of physics. In nuclear physics also, when you study the radioactive decay law, so decay is also an exponential function, decay of radioactive substances. That's where we study the decaying of different radioactive elements. And this function becomes very handy in studying those radioactive decay laws or understanding those decays. So that's where this function plays an important role. That's the exponentially decaying function or the exponentially growing function. So that's it for today. In the next lecture, we'll be giving just a brief touch about few more functions, one or two functions, and then we'll be starting with the introduction of vectors. And that's it for today, and we'll be meeting in the next class. Till then, take care and goodbye.